Alrighty, hope you're ready to go on a journey, because here we are, 6.5, trigonometric form of a complex number. Okie dokie, what are we going to be doing today? Plotting complex numbers in the complex plane, writing trigonometric forms of them, multiplying and dividing them, using de Moivre's theorem to find powers of complex numbers. It's going to be great. So let's start off with the complex plane. Hopefully at this point, everyone is used to or has seen graphing in the complex plane. Complex plane meaning that we have a real axis going where we would generally have the x-axis, and an imaginary axis where we would generally have the y-axis. And you plot exactly the same way that you would in a standard coordinate plane, the Cartesian coordinate plane, where you have a complex number that's written in this type of form, a plus bx, where a and b are both numbers, and I'm sorry, a plus bi, where a and b are both numbers. And you just plot AB as if it were a coordinate in the standard Cartesian plane. So, for example, if I had 3 plus 2i, to plot that, I go over 3 in the real axis, and I go up 2 in the imaginary axis, and I plot my point there. Or, if I have negative 1 plus 3i, that means I go over negative 1 in the real axis, and up 3 in the imaginary axis. And lastly, negative 2 minus i means I go negative 2 on the real axis and minus 1 in the imaginary. Right, so that's plotting in the complex plane. Hopefully that's just a refresher. Now, in order to work effectively with powers and roots of complex numbers, writing in trigonometric form makes that so much simpler. Okay, so if we can imagine a coordinate point in the complex plane, a plus bi, and I plot it basically the same way that I do in the regular plane, I can still have these same basic trig rules where a, the value I'm going over on the real axis, is in relation to kind of like cosine, and b, the amount that I'm going up on the imaginary axis, is kind of in relation to sine, and the distance from the origin to that point would be my hypotenuse, or my radius. So keeping that in mind, let's try to create the same rules that we had for things like vectors or trigonometric numbers in the regular coordinate plane. So we have this thing called the absolute value, and basically the absolute value of a complex number simply is just the distance from the origin to that complex number. Alright, so taking aside all of this more fancy mumbo jumbo, it's the distance from 0, 0 to the complex number. 0, 0 to complex. That's all that the absolute value of a complex number is, which, if we look back on this image again, that's also what we're going to refer to as r, the hypotenuse of that particular type of triangle. Okay, so let's see. If I have a complex number that says negative 2 plus 5i, how would I find the absolute value of that? Well, just like I said before, if I have negative 2 plus 5i, that means that I'm essentially just going to be trying to find the distance from 0, 0 all the way to this complex number, negative 2 plus 5i. Okay, so I'm going to be looking at the square root of 2 squared plus 5 squared. Okay, now technically this is negative 2 squared. So negative 2 squared is going to be a 4. 5 squared is going to be a 25. So I'm looking at the square root of 29. And that would be the absolute value of this complex number. Simple enough? I hope so. Alright, now let's take a look at how we can build the trigonometric form. Like we said, the a value, the value that you're going across on the real axis, is going to be related to the cosine. And the b value, the value that you're going up or down on the imaginary axis, is going to be related to sine. And r, we just spoke about, is like the absolute value of the complex number, or the hypotenuse of that triangle. So what we get is simply that this a plus bi complex form can be rewritten if I write a as r cosine theta and b as r sine theta. It's just r cosine theta, which was a, r sine theta, b, I, with I tacked on to the end, multiplying the b value, which I'm writing as r sine theta. So this is how we obtain the trigonometric form of a complex number. So if I have any particular complex number, z equals a plus bi, I can rewrite that with r times the cosine of theta plus r times sine I of theta. Right, just right here. It's exactly the same thing as we had written right on this page, with the exception of the fact that the r has been undistributed. See, the r is multiplying cosine, the r is multiplying sine. On our next page, where we have the formal definition, the r is just distributed into both of those. All right, so our a is r times the cosine, our b is r times the sine, and r again is the hypotenuse. Alrighty, there we have that. Now, let's see if we can manage to make this complex number into trigonometric form. Okay, my complex number is negative 2i. So the first thing I'm going to need here is the r value. So r is generated from finding the distance from the origin to that complex number, which means I'm going to be doing the square root of the a value, which in this case the a value is a 0, so 0 squared, and then add that to the b value squared, which is a negative 2 squared. So in this case, what I'm looking at is the square root of 4, which equals 2. So my r value is a 2. Okay, got that. Now, the next thing that I need would be the angle value, the angle at which I'm rotating to get to this complex number. Now this is very much like when we were talking about vectors and finding direction angles of vectors. The angle can be found simply by using the tangent function and the sides b and a. So the tangent of theta should equal b over a. So in this case, what do we have? The a value here is going to be a 0, so we're looking at tangent of theta equals negative 2 over 0, which we see is undefined. So where is the tangent function undefined? It's undefined both all the way at the top of the unit circle at pi over 2 and down at the bottom of the unit circle, 3 pi over 2. Now this imaginary number, if I were to sketch it out on a plane, would be directly down here at negative 2i. So we're going to go with 3 pi over 2, which is all the way down at the bottom of the unit circle. That's what our theta value is going to be. So now when I go forward and I try and write the trigonometric form of this complex number, where it would be r times cosine of theta plus sine of theta times I, what I'm going to do instead is write r, which is 2, cosine of 3 pi over 2 plus I sine 3 pi over 2. And that is my trigonometric form of this complex number. Easy enough, right? All I needed to do was find r and find the theta value. Then it was just a matter of plugging numbers in. Now let's see if I can take this complex number and put it into standard form from the trigonometric form. All right, this might be a slightly harder task to do. So let's take a look. Because the cosine is supposed to be negative pi over 3, and the sine is supposed to be of negative pi over 3, I can actually evaluate those two numbers. So the cosine of negative pi over 3 is just going to be 1/2. The sine of negative pi over 3 is just going to be the negative square root of 3 over 2. And then I can multiply the square root of 8 times both of these things. This also has an I multiplied to it, and there's a plus sign in between, and this is still getting multiplied by the square root of 8. So when I multiply the square root of 8, then things become, slightly messier. Square root of 8 over 2 plus, we got the square root of 8 times the negative square root of 3, this is multiplication, all over 2, and I. Now what I'd like to do is try and see if I can simplify this at all. Square root of 8 is 2 square roots of 2 over 2, and 2 square roots of 2 still being multiplied by negative square root of 3 over 2, but now I can simplify a little bit. Those 2's and these 2's, so that's the square root of 2 over 2 plus the negative square root of 6 over 1 times I. And there we have it. This would be how I would normally have written this complex number in standard form as opposed to the trigonometric form. So going from trigonometric form to standard form is much simpler. It's just a matter of evaluating the trigonometric functions and then multiplying in the distributed R value.
60% of the time, it works every time.
All right, now let's talk about multiplication and division of these complex numbers. It is going to be so much simpler to multiply and divide these things when they're in trigonometric form. So let's just suppose I have two different trig functions. I have one and another one. The only thing that's going to distinguish one from the other is that the first function will have sub 1 on all of its theta values and all of its r values, and the second one will have sub 2 on all of its theta values and r values. If I want to multiply these two things together, the process is quite painless. I simply multiply the two r values out front and then add the two theta values for the cosine and for the sine. Now this comes from some of the addition properties with trig functions, and that will be kind of like a little bonus later, a little bonus proof for some people later. And then for division of these two things, I will divide the two r values and subtract the theta values for the cosine, subtract the theta values for the sine. And this one, again, comes from that same idea, but from subtraction rules. So this is some really cool proof, but we'll be able to look at that later, possibly individually. So let's take a look at how we can actually apply this. I want to multiply these two complex numbers together. So multiplying these two complex numbers really shouldn't be too much of an issue, as long as some of the numbers work out pretty well. So my first thing that I have to do is multiply the r values. I have a 3 and I have a 2. When I multiply the r values, I get a 6. Okay, now what I have to do is add together the theta values for the cosine. So pi over 4 plus 3 pi over 4, that's 4 pi's over 4, or just pi, plus I sine, and then again add the theta values, pi over 4 plus 3 pi over 2, and that is pi. Done and done. It doesn't need to be more complicated than that. Now let's see if I can do some division. I'm going to divide z1 by z2, which means I guess I need to divide the r values. So that's 24 divided by 8, which is a 3. And then I don't add the theta values for the cosine, I subtract them. So 300 minus 75 is going to get me 225 degrees plus I sine, and again I subtract the theta values, 225, and that's it. I'm done. That is so much simpler than trying to take the standard form of two complex numbers and subtract or add them. Multiply or divide them. Now let's look at powers. Right. Raising something to a power, we know, is just repeated multiplication. So the rules for multiplying or to creating powers of these trigonometric complex numbers is simply multiplying the rules for multiplication and adding a multiple of 2, a multiple of 3. So the original function right here, when it gets squared, is when it's multiplying by itself, which we know when we multiply two of these functions, I need to multiply the r values, that's r squared, and then I add together the theta values. Because these values are the exact same thing, it's just 2 of the theta and 2 of the theta. But then what happens if I cube it? Well, that's the r squared being multiplied by the r function again. So again, I multiply r times r squared, which is r cubed, and then I again have to add all the theta values. 2 theta plus theta is 3 theta. 2 theta plus theta is 3 theta. So it just continues on and on and on like this. When I go to the 4th, it's going to be r to the 4th and 4 thetas. When I go to the 5th, it's going to be r to the 5th and 5 thetas. This pattern leads to De Moivre's theorem, right? A French mathematician who said, you know what, this is a pattern, it's going to happen every single time. If I'm raising a complex number z to the nth power, It's simply going to be raising the r value to the nth power and then multiplying the theta values by that power. Okay? So let's see it in action. I have 1 plus the square root of 3 times I, and I'm going to raise it to the 12th power. Now this is a binomial. If I wanted to take this binomial and raise it to the 12th power, it would be an extremely long and arduous process. But because of de Morgan's theorem, as long as I can put it into a trigonometric form, I should be able to do this quite simply. So the first thing I want to do is put it into trig form, which means I need the r value, which is going to be the square root of 1 squared plus the square root of 3 squared. So that's going to be a 1 plus a 3, the square root of 4, which is, you guessed it, dose. Cool, so now I have the r value. Now what I need to do is to try and find the angle value, which is going to be b over a. So I'm looking for square root of 3 over 1, and that'll be the tangent of theta. So I'm looking for where is the tangent square root of 3. Okay? If I look at that on a unit circle, I could pretty easily find out that theta equals pi over 3. So there it is. I have it. Now what do I have to do from this point? I have the r value and I have the direction angle value. So it should be pretty simple. I have 2 and then the cosine of pi over 3 and plus I sine pi over 3. Now that's not it. I now need to take this trigonometric form and raise it to the power of 12, which if I look at de Morgan's theorem, if I want this trigonometric function raised to the power of 12, that means I'm going to take the r value, which is a 2, raise it to the 12th power, and then on the inside, take the cosine of the theta value and multiply the theta value by 12. 12 times pi over 3. And I sine 12 times pi over 3. And then I will be done. So, what I need to ask myself is, what is 2 to the 12th power? Well, if I evaluate that, that's actually 4096. And then the cosine of 12 pi over 3, if I simplify that, that's just the cosine of 4 pi. And plus I sine, and again 12 pi over 3 simplifies to 4 pi. And there I have it. I have evaluated that. So now if I really, really, really wanted to, and I wanted to get a single number from this, the cosine of 4 pi is simply a 1, and the sine of 4 pi is a 0, so 0 times I is 0, so plus 0, and 4096 times 1 is 4096, and I can evaluate and get a single numerical digit for raising this this complex number to the 12th power in such a simpler way than trying to sit there and FOIL out 12 times all the repeated distribution involved in this complex number. Okay, that is it for today. Hopefully this was relatively painless. Remember to write down your questions, remember to do the assigned problems, and I will see you all in class next time.